This video is over the final section in Chapter 8. It's Section 8.8, Improper Integrals. Here's the definition of an improper integral. Basically, when we talk about a definite integral, the interval in which we're talking about, it must be a finite interval. And the fundamental theorem of calculus requires that that function is continuous on that given interval. Well, this lesson talks about integrals that do not satisfy these requirements. And the reason for that is because either one or both of their limits of integration are infinite, so either b goes to infinity or a to negative infinity. So that's this case. Or because the function has some sort of discontinuity within that interval. So there are two cases of improper integrals. This is going to be the first case. This is improper integrals with infinite limits of integration. So in this case, these are known as improper integrals, and the reason is because the function has some sort of infinite discontinuity. So there's some sort of vertical asymptote taking place. So when we are solving these, we apply limits. And I know some of you probably cringe a little bit when you think of the word limit, but really this is one of the more easy to understand ideas of limits. At least that's what students have expressed. So if you look at this particular example, we can see that the interval is from 1 to b of this function here, 1 over x squared. If we evaluate this integral, we end up getting negative 1 over x as the result, and then we apply the fundamental theorem of calculus to get this. Okay, so let's take a look at what this looks like. Okay, so what we are looking for is this shaded region here. And we want the region from 1 to infinity. Okay, so now b is infinity instead. So in order to evaluate this, I will simply integrate from 1 to b like we did previously, and we got this. But now we just apply the limit. And if I have 1 over infinity, this approaches 0, leaving me a result of 1. So this integral is the unbounded region now, so that's a little bit different. It's the unbounded region of the graph, and that results in an area of 1. Here it talks about different definitions of improper integrals. So there are 3 different cases here when we deal with infinite limits. So here the function goes to infinity. Here we approach infinity in the negative direction. And then in the third case we have negative infinity to negative infinity. I would take a moment and pause this video and read through this because this is pretty important. If the limit exists, then we will say that the function or the integral converges. On the other hand, it will diverge if the limit does not exist. And then finally, it talks about the third case, whether or not it converges or diverges. So let's just jump into an example. In this first example, it says determine whether the improper integral diverges or converges. and then evaluate the integral. This should say if it converges. So I provided a graph for you just so you can see what's happening. We're interested in, so here's the graph of this function, but we're simply interested in the region from 3 onward to infinity. We want to evaluate that area. So in order to evaluate an improper integral, what we'll do is we will apply the limit. So this will give us the limit as b approaches infinity, because we're going to let this be b, remember, of the integral from 3 to b, and we'll have the exact same integrand. Oops. And then we just evaluate this with an upper limit of b. Now, evaluating this, it shouldn't be too difficult. Let's let u be x minus 1, going for a u substitution. So if that's the case, then du is just 1 dx. So then I will integrate u to the negative power of 4, just making that a negative exponent. If I integrate this, I get negative 1/3 u to the negative power of 3. So let's go ahead and plug u back in. So this becomes the limit as b approaches infinity of, when I evaluate this integral, I got negative 1/3 times the quantity x minus 1 cubed. And I'll evaluate this from 3 to b. Okay, so now we just apply the fundamental theorem of calculus, plugging in the upper limit and then subtracting and plugging in the lower limit. I continue to write this limit notation until I apply the limit. So this becomes b minus 1 cubed, and this will become plus, because minus and negative is positive, 1/3 times 3 minus 1 quantity cubed. All right, so moving onward, just going to simplify this a little bit. Oops. This here becomes 1/24. All right, so let's evaluate this integral here. If b is approaching infinity, and I plug infinity in here, this is going to end up being 3 times infinity, which is just infinity. So recall, if I have negative 1/infinity, this is just approaching 0. So this is 0. So the limit of this is simply itself. So we find that this limit is 1/24. So to conclude this problem, since the limit does exist, we will say that this improper integral converges because the limit exists. And that integral is equal to 1/24. And that's it. Let's look at another example. Here it says determine whether the improper integral diverges or converges. Evaluate the integral if it converges. Okay, so looking at this, now we have a lower limit of negative infinity, so we can see right away that this is an improper integral because one of the limits involves infinity. So in this case, if I want to integrate this, at some point, I'm going to have to apply integration by parts. Okay, so recall integration by parts is the following. It's the integral of u dv is equal to uv minus the integral of v du. Okay, so recall we need to find dv, and we also need to find u. Remember that dv is often the more complicated portion of the integrand, and we have to be able to find the integral of it. So let's let dv be e to the negative 4x, and then that means u is x. If this is dv, if I integrate this, oh sorry, there should be a dx here. If I integrate this, I end up with negative 1/4 e to the negative 4x. If u is equal to x, then du is equal to dx. Okay, so now we are going to plug these values in here. So when we do that, we have the integral of u dv is equal to u v minus the integral of v du. Okay, so let's clean this up a little bit. So this integral will be equal to, cleaning this up, I get a negative 1/4 x e to the negative 4x. This will be plus, moving the 1/4 out, plus 1/4 times, when I integrate this, I've already done that once before, this will be negative 1/4 e to the negative 4x. Now I'm gonna, even though this is an improper integral, overall I'm dealing with a definite integral, so I'm not gonna use the plus c here. Continuing my simplification process, combining these, I get negative 1/16 e to the negative 4x. And I can clean this up a little bit more so that when I apply my limit, it's maybe a little more manageable. So I'm going to just take out an e to the negative 4x. So then I'm left with negative x over 4 minus 1/16. You can take out a negative too if you want. It doesn't really matter. Okay, but here is the integral. All right, so now I'm going to apply the limit. Okay, so just like the previous examples, when I do so, I'm going to let b approach negative infinity. So now this is b. Okay, and just plugging in what we have over here, e to the negative 4x is equal to, let's see, okay, and then we're going to evaluate this from b to 0. Okay, so plugging in 0 should not be a problem. So I'll have, this is just e to the 0 times, if I plug 0 in here, this goes away. So I'll multiply this by negative 1/16. Then I will subtract and plug in b. So this is e to the negative 4b times negative b over 4 minus 1/16. Okay, so onward. Oops. Okay, this e to the 0 is just 1, so this gives me a negative 1/16. Let's analyze this over here. Okay, so I need to plug in a negative infinity here and a negative infinity here. So really what happens is this gives me e to the power of infinity. And if I have e to the power of infinity, that's really equal to infinity. So essentially, I'm going to be subtracting infinity. Okay, so anything minus infinity is negative infinity. So what this means is the limit does not exist. So since this limit does not exist, we will say that this improper integral diverges. And that's it. So that wraps up examples involving improper integrals with infinite limits of integration. So now let's talk about the other type of improper integral, and those are the ones that involve infinite discontinuities. So now these are the examples where there's some sort of discontinuity at or between the limits of integration. So here's an example. It says, or the three different types rather. So our function is continuous on the interval from a to b, where a is included, but there is a discontinuity at b. So there's probably some sort of asymptote there, vertical asymptote. So the way in which we solve this is the same, but the graphs essentially just look different. So this example is where the other endpoint is discontinuous, and then this is an example where there's some value within the interval that has a discontinuity. And this information here is basically the same type of thing. So let's look at a couple examples involving this type of discontinuity. In this example, it says, determine whether the improper integral diverges or converges. Evaluate the integral if it converges. Okay, so here I've provided a graph for you once again of this function 10 over x. And we are only interested in the interval from 0 to 5. So if I look at this, I'm interested in this area here. And you should be able to tell that there is a discontinuity here. We have a vertical asymptote. Okay, so wherever that discontinuity is, that's where you're going to focus on this being B. Okay, so I'll show you how this is a little bit different. Okay, so the way we set this up is still by applying a limit, but now we need to focus on which direction we're coming from. So this is b approaching 0 from the right. And this is because the function is approaching 0 from the right-hand side rather than from the left. Okay, so that's basically the difference. Okay, and then we're going to integrate this function from b to 5. So when we do, we will carry the limit, b approaching 0 from the right. When I integrate this, it's not terrible. It gives me 10 times the natural log of x, and we will evaluate this from b to 5. So our limit, as b approaches 0 from the right, applying the fundamental theorem of calculus, this becomes 10 natural log of 5 minus 10 natural log of b. Okay, so in this case here, If I look at this, I can't plug 0 in anywhere here, but I can plug 0 in here. Okay, so this becomes 10 natural log of 5 minus 10 natural log of 0. And let's analyze this for a moment. All right, clearly this results in some value, but let's address this part here. The natural log of 0 is undefined. Let me remind you that this is the graph of the natural log, and the natural log of 0 does not exist. So, because of this, this piece here is undefined. And if that's the case, if this is undefined, then this area here this is said to be divergent. Okay, so since this is undefined, we can't subtract something from this. So this means, or therefore, this diverges. Okay, because the limit does not exist. Here's the final example. It says determine whether the improper integral diverges or converges, and evaluate the integral if it converges. And once again, typo. Okay, so the graph is provided for you. We're interested in the interval from 0 to 8, and you should be able to tell that there is a vertical asymptote here. Okay, so setting this up just like before, since there's an infinite discontinuity on the right-hand side, this is going to be b. So our limit as b approaches 8 from the left now, so we are approaching 8 from the left of the integral from 0 to b Okay, so we need to evaluate this integral. Let's let u equal 8 minus x using a u substitution. So then du is negative dx. So when I evaluate this integral, I'll have negative u to the negative 1/2. So this will give me a negative 2u to the 1/2. All right, so this becomes the limit as b approaches 8 from the left of, let's see here, 3, just moving this to the outside, 0 to b, 8 minus x to the negative 1/2 dx. Okay, onward. When I evaluate this, I end up with negative 6 times the square root of 8 minus x. Just applying this here. And we will evaluate this from 0 to b. Okay, applying the fundamental theorem of calculus before applying the limit. This will become a plus. And that's just 8. Okay. All right, so now plugging in 8, this is 8 minus 8, which is just 0. So this goes away, 0. Over here, there's nothing to plug in. So this is 6 root 8 And if we want to reduce this, we can. Remember, this can be written as a perfect square times a non-perfect square, which is 2 root 2. So 6 times 2 root 2 gives us 12 root 2. So this tells us that the limit does exist. Therefore, this improper integral converges, and its value is 12 root 2. And that concludes section 8.8.